In this video, we are going to learn or remember the reaction concept of reaction extent. It is a performance indicator, but it is going to be used instead of a familiar concept of conversion. So we have more than one reaction, R1 and R2. In the top row, I wrote the reaction rates, the stoichiometry matrix, and reaction rates for individual components as we have written already. And the transpose of this is sometimes more convenient. In the second row, we have the transport stoichiometry matrix or tensor. Then, of course, the reaction network has to go to the other side of the matrix, and we have the column vector of reaction rates of the individual components. So we are carrying out this analysis for a batch reactor. Here is our design equation for a batch reactor. dNA over dt is equal to Ra times V, and I'm going to integrate this expression between the initial and Na minus Na0 I would like to have a common function that is going to represent that particular reaction. So instead of Ra, I'm going to write R times nu Ai and integrate with respect to time, and this should be equal to an extent of the reaction psi 1 summation over all the extents of the reactions that are involved, that involve component A. So extent of reaction is the term that defines how many moles of component A is produced from reaction 1, how many moles of component A is produced from reaction 2, or vice versa, consumed. So this is going to be a strong function of the reaction stoichiometry, just like the reaction rate. So we are removing the rate concept and generating an algebraic equation by simply relieving the derivatives from the batch reactor analysis. And this is going to be useful also when we are performing a CSTR analysis. Let us discuss these concepts with an example of a complex reaction network, 2A plus 3B going to R, B plus D going to S. R1 is given as K1Ca times Cb, and it is represented by Xi1, and R2 is K2Cb Cd, and it is represented by Xi2. So Xi1, just to be sure, it has the units of moles. This has the units of moles, while R1 has the units of mole per volume per time. So let us write the overall balance equations. NA0 minus NA, how much A is consumed, is going to be 2 psi 1 and B0 minus NB will be 3 psi 1 plus psi 2, 3 psi 1 plus psi 2, and D0 minus ND is psi 2 only. And let's write for the products also. And R0 minus NR is minus psi 1 because it's on the product side. And S0 minus NS is equal to psi 2. Now let's take the derivative of each and every one of those to express all of the species number of moles in terms of only two parameters. dNA over dt will be equal to minus 2 d psi 1 over dt. dNB over dt will be equal to minus 3 d psi 1 over dt minus d psi 2 over dt. dND over dt will be minus d psi 2 over dt. Now as you see, we are reducing a 5-dimensional space into a 2-dimensional space, psi 1 and psi 2. In a single reaction network, we were using conversion to bring a multidimensional component space into a one-dimensional conversion space. Here, in a complex reaction network, we are converting a multidimensional component space into the space that is defined by the reaction extents. So let us write the derivatives here as well. dNR over dt is going to be d psi 1 over dt, and a dNs over dt will be equal to d psi 2 over dt. Now we are going to introduce the design equation. Instead of dNA or dNR, you're going to write the reaction rate with respect to R. So this is going to be RR times V, right? RR times V. What is RR? It is R1 times nu R, that is equal to R1 times V This is going to be R2 times V and we are going to introduce concentrations, the rates in terms of concentrations, K1 times Ca. Ca is Na over V. Let's make sure that we have the note here that this is a constant volume reactor. Okay, K1, I will write Ca times Cb times V. Ca is Na over V. Cb is Nb over V. And Na and Nb are expressed in terms of reaction extents. We're going to substitute for those as well. Let's write for S for the completeness. This is K2 times Cb Cd times V, and this is Nb over V, and this is Nd over V to be substituted. Using our cleaned up version of our board, let us define Na, Nb, and Nd in terms of Psi1 and Psi2. Na is equal to Na0 minus 2 Psi1. Nb is equal to Nb0 minus 3 Psi1 minus Psi2. Nd is equal to Nd0 minus Psi2. So I'm going to substitute this into these differential equation. D Psi1 over dt is equal to K1 Na, Na0 minus 2 Psi1 times Nb, Nb0 minus 3 Psi1 minus Psi2 times V divided by V square. V's cancel, and I'm left with only one V. We have d Psi2 over dt. We're going to substitute these terms. K2 times Nb, Nb0 minus 3 Psi1 minus Psi2 times Nd, Nd0 minus Psi2 divided by V square multiplied by V divided by V. Volume is constant. So I have two coupled ordinary differential equations to solve with the initial conditions. At time t is equal to 0, psi1 is equal to 0, psi2 is equal to 0. Solution of those coupled ordinary differential equations are not trivial. It will require numerical tools, and I refer you to numerical tools such as MathCAD, MATLAB, or Polymath to solve this set of equations. Of course, when numerically solving these equations, we will need numerical values for Na0 and B0 and also the other constants. But once we have psi1 and psi2, we can solve for all the other concentrations such as A, B, C, as well as R and S.